Okay. Okay, before I start, have you seen your assignment 1 on eLearn? Have you opened and seen the questions? Leon? Right? Started already? Okay, good. So you have plenty of time for your assignment 1, yeah? So if I'm not mistaken, the due is on 13, if I'm not mistaken, 13th of May. There's plenty of time since today is only 26. So you have like about 3 weeks or so to finish off your assignment 1, okay? So let's continue with the new topic. We started discussing about carrier transport phenomena, okay? Which revolves around the movement of carriers in different conditions. So let's just recall on the dominant transport mechanism of our carriers. So what are the two mechanisms our carriers move in the semiconductor? How do they move? In other way, anyone? Okay, drift and diffusion. Okay, drift and diffusion are the two mechanisms by which the carriers move that we started discussing yesterday. So let's just recall a little bit before we move on to the details. So when do we have drift component in our semiconductor? When do we have the drift component in our semiconductor? When do they start drifting? They here means the carriers, okay? When do you get drift? Okay, when there is an electric field present. Okay, good. Voila. When there's an electric field present in the semiconductor or applied or imposed on your semiconductor material. So how about the second one? When do you have diffusion? When do you have diffusion component in your semiconductor? Anis, ada? Anis Amira? I'm just browsing through the names. Anis Amira, are you here? Ah, okay, Fatul said different concentration. Okay, what do you mean by that, Fatul? Different, how do you tell the difference? Or between, how do you come to the difference between concentration? Maybe you can elaborate a bit? Boleh unmute, Fatul? Let's go ahead. Bila kita ada diffusion component. Betul? Anyone would like to add on that? Anyone would like to assist? when do we have diffusion component of our carriers? Kuatin? Kuatin? All right, concentration gradient. Okay, concentration gradient. So the difference in concentration here means concentration gradient between two regions, okay, two neighboring regions, if you like, okay, two side-by-side regions. So we're gonna go into the details later on. And we have also discussed briefly about mobility dependence on doping, where we have discussed on the difference or the change in the mobility of our carriers uh, at low doping level and at high doping level. So for example, we discussed yesterday what is the value of your mobility of, say, electron or hole, say at 10 to the 16 versus 10 to the 18, okay? And then we have come to the conclusion that when you have increased doping level or dopant concentration in your semiconductor material, you're going to have more and more scattering by the impurities. And the impurities here means the dopants, right? Either it's phosphorus or boron or some other dopant material in the lattice, okay? So we would like to extend that a little bit more to see how does the mobility on the y-axis in this case, just like what we discussed yesterday, how does it depend on doping and temperature at the same time, okay? So we have seen an inverse relationship, if you like, from our previous discussion, from our previous page. You can come back to this and you can see an inverse relationship overall between the mobility of your carriers and the doping level, whether it's NA or ND, right? Even though you hardly see any difference between the mobility in the low doping region, say here 1014 to 1016, you barely see any change in the mobility because they are low doping level to begin with, right? Low to moderate, okay? If you like, more low to moderate, because 1016 is typically considered moderate, but if you talk about 14, we can say that it's a low doping level. But if you go to beyond 17, you can see that it's approaching high doping level or heavily doped region, okay? So let's see. So now you can see the dependence of the mobility on both doping and temperature, where on this graph you can see your doping increases as your doping increases in this way, okay, where doping changes from 10 to the 14 for the upper curve, up to 10 to the 19 for the below curve, right? 10 to the 14 for the top one, up to 10 to the 19 for the below one, right? And the rest is just in between, going 15, 16, 17, 18, okay? And you can see this, okay, this is plotted against temperature to begin with, right? Temperature is on the x-axis, and do we see, if you look at, if you forget the temperature, for example, just omit the temperature first. If you look at this arrow, right, to correlate the relationship between mobility and doping level, do you see the same relationship that we discussed yesterday? Okay, try to see again. It's not that straightforward though. Forget the temperature on the x-axis. Just look at the mobility on the y and the doping level in the graphs. Okay, do you see the same relationship between mobility and the doping level in this graph? If you compare to the previous graph yesterday or just now, it decreases, right? So it decreases. So essentially, it reflects on what we discussed yesterday and just now. So which says if you increase doping level either NA or ND, your mobility decreases. So sama aja. It's just that this second graph is represented in different ways, okay? Because it's plotting mobility against your temperature, okay? But the doping level is inside the graph, but essentially the message is the same. And it's not like something different already, right? It's not like different relationship. It's exactly the same thing, but plotted against different parameter, and you get to see the slightly different thing. But the message or the conclusion is still the same. Where when you increase your doping level from 10 to the 14 up to 10 to the 19, for example, your mobility decreases, okay? Your mobility decreases. But you can see something else as well on this graph, where when you vary the temperature, when you increase the temperature, to be exact, or we can say that we're going from the left to the right, from 100 Kelvin on the left up to 1000 Kelvin on the right, you can see different relationships or different shapes of the curve at different categories of doping levels, okay? So what we see at a low doping level, you can see that when your temperature increases from left to the right, you can see that your mobility decreases, okay? So low doping level here, for example, you can see from this at least the top 2 or top 3 curves, 10 to the 14, 10 to the 15 or 16 there, 15, 16, and 10, 17. Even though 70 is not considered as low doping, but you can see at least the top 3 curves are showing inverse relationship between mobility and temperature, okay? On the other hand, if you move to heavily doped or high doping level, let's just call this heavily doped region, 18 and 19, heavily doped, okay, or high doping, you can see high doping level. You can see the shape is different, right? So it's a bit dome in the shape, so it goes up a little bit, it increases a little bit up to a point, then it starts to decrease, okay? It starts to decrease. For example, if you look at 10 to the 18, you can see a peak at somewhere about 300 or 250 Kelvin, perhaps 240 to 50 Kelvin, okay? So right there, and the peak for 19 is a bit different, it's shifted to the right, okay? And then it goes down, right? It goes down as you increase the temperature, just like what you see on the low doping level case, right? The top 3, for example. So why is it the case? For lightly doped samples, 10 to the 14 up to, you can see 16, 15, 16, lattice scattering dominates, right? Lattice scattering dominates. So lattice scattering here refers to your silicon lattice. Okay, the silicon lattice, which is the host or the semiconductor material itself, right? At low doping level, the lattice scattering dominates and mobility decreases as the temperature increases. Okay, so that means if you have an increase in temperature going from the left to the right, going from the left to the right, as you go to the right for this particular case, for example, you're going to have your lattice scattering, the silicon lattice gets more and more scattering, right? So they had a bunch of scattering, and as a result, as we discussed yesterday, when you have scattering, that will translate into a hindrance or a resistance to the motion of electrons or your carriers, okay? So remember, the mobility here is the speed or the ease of motion of your carriers, okay? Speed if like. Lagi tak ada resistance, lebih senang dia move around or lebih laju, okay? Or on the other hand, if you have a lot of what you call blockage or a lot of hindrance or a lot of resistance in the motion within the way, then you're gonna see or you're gonna expect a lower mobility of your carriers, okay? So in this case, when you move to the right, we're gonna see more and more lattice scattering, comes into the picture, and as a result, the mobility decreases. Okay. On the other hand, for the heavily doped sample, for those which are below here, okay, the effect of impurity scattering is most pronounced at low temperature. So the effect of impurity scattering is most pronounced at low temperatures. So that means we already discussed yesterday when you talk about this relationship, we have come to conclusion that there are more impurity scatterings at high doping level, or when you go for heavily doped, right? So this impurity scattering in the lattice dominates at low temperatures, okay, at low temperatures. So that means you're going to see the effect clearly or more significantly at low temperature, which can be represented at as the left region, if you like, on the low temperature side. So this is where the impurity scattering dominates in the heavily doped semiconductor, right? The mobility increases as temperature increases, right? The mobility increases a little bit as the temperature increases, which is represented by the middle region, where you have some increase, a slight increase in the mobility of your carriers as the temperature increases. For the heavily doped samples, you can see at 18 and 19. Then, if you keep increasing the temperature, you're going to fall from the left to the right. Mobility decreases with increasing impurity concentration because of enhanced impurity scattering. Oh, this one is still impurity scattering. Okay, impurity scattering. But when you go to the right, okay, the impurity scattering there in the last sentence is now can be represented by this region, heavily doped region. Right? It's not talking about left or right yet, because it's not dependent on the temperature yet, right? So what I'm going to say is, if you're operating your semiconductor on your left at low temperatures, the mobility will be limited or will be dependent on impurity scattering of the heavily doped semiconductor. On the other hand, if you increase the temperature to say 400 and above Kelvin, so you're going to see the mobility reduces due to enhanced lattice scattering. Okay, due to enhanced lattice scattering. So this can be summarized or can be represented by this inset. Okay, if you tengok kat sini, the relationship is like that, dome shape. So here on the left is for the low temperature. So this is log. If you plot log of mu against log of t, okay, which is essentially mu against t, but in the log form, you're going to get impurity scattering dominating low temperatures of the heavily doped semiconductor, while lattice scattering dominates high temperature in the high temperature region of the heavily doped semiconductor. And this is not seen in lightly doped or moderately doped semiconductors, because the relationship between mu and t is inverse in nature, okay, and it's dominated by impurity scattering for all the cases, okay, across the temperatures. Okay, so for the low lattice scattering, sorry, not impurity scattering, lattice scattering. So if you talk about lightly doped, you are only talking about lattice scattering as you vary the temperature, okay? But if you talk about heavily doped semiconductors, you need to be talking about two scattering mechanisms, right? Impurity scattering at low temperatures, and lattice scattering at high temperatures, okay? So ingat, so a lightly doped semiconductor, only lattice scattering dominates at increasing temperatures. Tapi untuk heavily doped, you're going to have impurity scattering dominates at low temperatures, but lattice scattering dominates at high temperatures. Okay. So let's have a look at another representations of the same thing. You can see mu on the Y. So as I said, it can be represented by mu N or mu P, or you can also write these as mu E and mu H. As long as you're consistent, that's totally fine. against temperature in degrees Celsius, right? So you're also seeing pretty much the same relationship within the range of negative 50 degrees Celsius up to 200 degrees Celsius. Okay, so you are not seeing any obvious dome shape here because you're talking about low temperature region, right? Low temperature region only. Okay, but you still get to see the mobility reduces at a high doping level, right? Either you're talking about electron or holes. So now is a dependency of mobility of your carriers for both electrons and holes. Both are plotted for three different semiconductor materials against impurity concentration or against doping, if you like. So here we're talking about germanium, we're talking about silicon, you're talking about gallium arsenide. Okay, so let's have a look at, for example, if we talk about, say, 1 times, or maybe 1 times 10 to the 17. Okay, let's have a look at 1 times 10 to the 17 of doping concentration. So what do you get for electron mobility in germanium? Okay, coba tengok. Look at the top graph. What do you get as your electron mobility in germanium at 1 times 10 to the 17? What do you get? Let's just have a look at electrons. Forget your holes first. What do you get for germanium? What's the value there? Anyone? Germanium 1 times 10 to the 17. Berapa tu? Anyone? Come, let's do some reading on the graph. Peshwan, what do you get? Peshwan? Germanium electron 1 times 10 to the 17. Anyone? Peshwan? Senyap ni semua? Okay, that's about what? 2.5. Let's see. Germanium 1017, 1, 2. Yeah, that's about 2.5, right? So 2,500. Okay, 2,500, right? 2,500. All right, so let's now have a look at silicon. Electron, silicon, 1 times 10 to the 17. What do we get? Let's discuss a bit. Anyone? Shalini? V Shalini? Too easy, right? Ke semua tak nak jawab sebab senang sangat soalan saya? Is it too easy? Now what do we get? Silicon, electron 1 times 10 to the 17. 1,000, right? Yeah, that's close to 1,000. Okay. Oops, sorry. 1,000. Okay. How about the last one? Gallium arsenide. Same thing. Electron, 1 times 10 to the 17. What do we get? Gallium arsenide. 4, perhaps, right? Is it close to 4,000? rough, huh? Just rough figure. The exact one you have to see the actual one, right? So this is just for comparison. Close to 4,000, let's say. Okay. So from these three values, which one has the fastest one? If you talk about mobility being the speed and ease of movement, which semiconductor has the fastest mobility of electrons at this particular doping level? Again, simple question. Betul ke, Pala? Germanium. Gallium arsenide, right? 2,500 for germanium, 1,000 for silicon, about 4,000 for gallium arsenide, isn't it? So that's why is this important? This mobility will be playing an important role when we talk about fabrication of transistors. Okay, transistors, especially if you're talking about high-speed transistors. High electron mobility transistors, transistors which drive switching of your devices. Okay, switching on off, like cepat. Like you want the switching to take place very fast, isn't it? You want the frequency to be very high, isn't it? So that boils down to the mobility of your carriers. Okay, so in this case, you should expect your transistors fabricated based on gallium arsenide to perform or to outperform the rest, the remaining two, silicon and germanium. Okay, so that's why you're going to see high-speed transistors are usually made from gallium arsenide due to the electron mobility in the transistors or in the semiconductor material. And you cannot see holes beating electrons in any case. Okay, that's why electron kita guna as your dominant carriers, as your majority carriers in transistors. Okay, so that's the significance of this one. That's the significance of this graph and these questions. Okay, so saya tanya soalan yang simple ya, so that you can figure out the numbers, and eventually that's the significance of those numbers. Okay, so now let's continue with drift and diffusion. So up to this point, we have considered drift, transport of electrons. So we have discussed that drift will be there if electric field is around, right? Or electric field is applied, or electric field is imposed to the semiconductor material. So the previous development applies for hole as well. So it's not only for electrons, it's also for hole, leading to a generalized expression of current flow due to drift. So remember when I talked about drift yesterday, I said whenever we have movement of carriers associated with drift, either it's electrons or holes, there'll be current associated with the motion. Okay, in this case, the current flow due to drift consisting of two currents flowing in the same direction. Okay, so what does it mean by this? So we're talking about the current J, current density associated with the flow of electrons and holes by drift. Okay, and this current density can be divided into two parts. The first one is due to the presence or due to the movement of electrons, and the second one is due to the movement of holes at the same time, right? Depending on which one is majority and which one is minority carriers. So as we discussed yesterday, the J can be summarized as your conductivity times electric field. So now we're coming back to this. J is equal to sigma E, conductivity times E, and you can break those down into two parts. Conductivity, which is due to electrons, and which is due to hole in the presence of the same electric field, right? So then you can break the J into JE plus JH. You can also write this in the form of Jn plus Jp is okay as well, as long as you're consistent, right? And Je is given by NQ mu E, right? NQ mu E, N we can write down as Q mu N E. So where your first part there is given by NQ mu, right? NQ mu, which is electronic charge times electron mobility times density of electrons times electric field. So that will make your JE, right? And the second part is JH. And again, you need to use the same calculation where your the first part is given by Q mu P, which contributes to this H, and then electronic charge times mobility of hole times density of holes times electric field. Okay. So let's have a look at the motion that we discussed yesterday when we look at animation on PV education. So you can see here that the movement of electrons, the red particle is in the opposite direction of electric field, and the movement of holes, the blue particle, is in direction of electric field. The electron opposite, hole same direction, right? So you're gonna get currents associated with this motion as JE and JH. Okay. So tengok ke sini ya, look at the direction there. JE and JH, right? So note that your JE is in the opposite direction of electron flow. Sebab current is in the opposite direction of electron flow, so therefore you're going to get your JE is to the left direction, right? And JH, on the other hand, is in the direction of electric field, which is also going to the left. Okay? So you have two different current densities moving to the left. So drift current density can be summarized as this, as we just calculated. Okay, you can factorize that if you want. You can represent that as Q or E. Sama aja. If you write down E is okay, Q is okay as well. Either one's fine. Where the first part here, sigma is conductivity of the semiconductor material, and conductivity is given in the units of the inverse of ohm cm. Okay, ohm cm. Itu kita discuss the curve of resistivity against doping level. Remember, resistivity against doping level, Na or Nd, and your doping, your resistivity is given by ohm cm, the label on the cassette before you take the wafers, and the conductivity is just the inverse of this resistivity. Okay, resistivity 1 over resistivity is conductivity, so that's why the unit is inverse. So it's a function of electron and hole concentrations and mobilities. Mobilities are a function of impurity concentration, so that's why we have discussed about how does mobility depend on your impurity concentration and conductivity, and yeah, right? Or in the last few pages. And also is dependent on temperature as well. Once we discuss about the low doping level cases and high doping level cases, right? For a given temperature, mobility decreases with increased impurity concentration because of enhanced impurity scattering. But remember, when you discuss about heavily doped semiconductor, you have to discuss about this dome shape relationship, okay? Where the left-hand side is dominated by impurity scattering, IS, if you want to summarize that, and on the right-hand side is dominated by lattice scattering, LS, okay? So let's do a few questions before we move on. Let's just do 2 questions perhaps and see whether you have time for conductivity and others. So let's have a look at the first question. Example number 1. Consider a gallium arsenide sample at 300 Kelvin with doping concentration of Na equals 0, Nd equals 1016. This is just for simplicity, yeah? So your Na is 0, your Nd is 1016. What is the type of gallium arsenide used in this case? P-type or N-type? What is the type of gallium arsenide used in this case? P-type or N-type? N-type. All right, Bala say N-type. Anyone says P-type? No one says p-type. Okay, Bala, why is it n-type? You can unmute yourself, Bala.
Because the donor concentration is 10 to 16 and the acceptor is 0, doctor.
Okay, so what is the majority carrier in this case? Electron or hole?
Electron.
Okay, what is the doping concentration of electron in this case? Others can answer as well. What is the doping concentration that you get for your electrons in this case? Saya soalan senang je, just to recap. There's a reason for this easy question. There's always a reason for easy questions. 10 je, 10 to the 16 as well. Right, so remember last time we talked about N can be approximated as ND. I want to recap the previous concept. Okay, N can be approximated as ND, or you can in fact say that N equals to ND in this case. Assuming, what do we assume here? To be able to say that N equals to ND. What's the assumption at hand? Or what is the assumption in mind? Apa assumption yang kita pakai to be able to say that N can be approximated as ND or N equals to ND? Just to recap the previous concept as well. What do we assume? Anyone? Apa yang kita assume last time? To be able to say that N equals ND, P equals NA. What was the assumption that we make? Molar of I. What is it? I. The word is I. I nak recap the previous concept so that you can always be on track. Fatin, intrinsic, not intrinsic, because it's dope in this case. What do you assume? Apa assumption? My question is, what is the assumption that we hold in order to say that N equals to ND? Saya bagi lagi hint kat depan ni. 100% of I. Ni senang, kau tak boleh jawab ke? I don't know. 100% of I. We assume 100% of I takes place.
Ionization.
Exactly. Ionization is the assumption, okay? We assume 100% of the dopants ionize. What happens if only 90% is ionized? What do you get as your N? A bit difficult, but not that difficult. If you assume 90% ionized, what do you get as your N? We're not discussing on the drift yet, just the previous concept. But on the drift question, I want to make sure that everyone is on the same page. We assume that, okay, you are questioning that. We assume that N equals to ND, right? If it's 100% ionized, or 1 times ND, if you like. If it's not, if it's 90% ionized, N is, you can see that N is about 0.9 of ND. Okay, then you're going to get 9 times 10 to the 15, isn't it? In this case, 9 times 10 to the 15. Unless otherwise stated, you can assume that it's always 100% ionized. Unless saya cakap is 80% ionized, then you have to times 80% with 10 times 10 to the 16. Okay, so that's the important assumption that you shouldn't miss at all. Okay, now assuming 100% ionization, I'm not talking about drift yet, even though this one is for drift. I'm still talking about the previous concept so that everyone is on the same page. Your N is equal to 10 to the 16. What is the level of your minority carrier concentration? The question can be like that, right? Before you go to drift. 10 to the 4, is it correct, Bala? You are using the right concept, but in this case, look at the material. gallium arsenide, right? Then it's no longer 10 to the 10. You have to revisit the value of Ni then for gallium arsenide. Tapi kalau silicon is the question, then you are right. Okay, it's just 10 to the 20 divided by 10 to the 16. You're going to get your minority as 10 to the 4. Okay, so the concept is correct. Law of mass action. Don't miss that. Don't forget that, right? So see, the question is about drift, but the very same information can be also extracted or can be also stretched to ask about some other previous concept that we've discussed. Assume complete ionization. See, this one is stated already. And assume electron and hole mobility is given in table 5.1 below. Calculate the drift current density if the applied electric field is 10 volt per centimeter. Your E is given already, right? So apa soalannya? Calculate the drift current density. So what are the parameters here? Or what is the parameter that you have to calculate here? Drift current density if the applied electric field is E equals 10 volt per centimeter. Boleh ya, semua dah ada kat next page ya. So I just would like you to understand, even though the answer is given, please understand the concept first, right? So now you can see the way you answer. Let's just finish off with this calculation, I think, then we will continue tomorrow with conductivity, right? Which is the inverse of resistivity as discussed. So in this case, remember your ND is way higher than your NA, or your NA is not even there at all, okay? Ada NA pun, you don't include any dopant from acceptor atoms. So your ND is only present. There's no Na to begin with. The sample is N-type in nature. The majority carriers are electrons. Therefore, N is equals to ND. Okay, below you dapat questions like this. Even though it's on drift, even though it's on diffusion, you always have to start with this in mind. If you're clear with this first thing, then the rest should be straightforward. Kalau yang the first line is still confusing for yourself, then the rest may be tricky. They're not tricky, but it may appear tricky to you, right? So even though the information is not as crucial, the above here, just write down as well. ND, therefore, is N-type, therefore, electron is majority carrier. These can also ask you about the Fermi level as well. Okay, so if this is the case, where is your Fermi level in the Venn diagram? How would you sketch? Even though there's no specific value to begin with, where would you sketch your position of Fermi level in this case? If it can ask, if asked about the Fermi level as well, how would you draw that for this particular material? VC, betul ke Bella? Where's your Fermi level position? VC ke EC? EC, right? Near conduction band edge, right? Below the below EC, near to the EC, near to the EC. How near? How do you determine if the question stretches a little bit more? How do you determine how near is it? Is it like far away, even though it's relative though? Is it very near or not so near? That will be dependent on your doping level, right? So remember last time we talked about the concept of degeneracy. If you go higher and higher in terms of doping level, the EC is going to, the EF, sorry, is going to be nearer and nearer and nearer into EC until the point when your N is equal to or more than the NC, value of gallium arsenide in this case. Okay, then it's going to go into EC. Dia masuk ke atas, It even exceeds EC, Right, that's not the point. The point is on something else. But let's revisit the previous concept based on that. So how to do next? The minority carrier concentration is given by P equals to Ni squared over N, law of mass action, exactly what we discussed. And Ni for gallium arsenide is given as 1.8 times 10 to the 6 squared over your ND, because your ND is now N, assuming 100% ionization. If it's not 100%, then it's totally different. If it's 90%, then you have to replace the denominator with 9 times 10 to the 15, right? Unless otherwise stated. Kalau tak cakap apa-apa, assume 100% ionization. Or you may want to write, assuming 100% ionization, therefore, blah, 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 right? So therefore, your P is 3.24 times 10 to the minus 4 per centimeter cube. Okay? So for this extrinsic n-type, so extrinsic, tadi bukan someone mentioned intrinsic. This is not intrinsic because it's dope. Extrinsic n-type. The drift current density is given by J drift. Okay, go back to the equation. J drift equals to J drift of electrons plus J drift of holes. Okay, remember the two components? Okay, you start off with both first, but since your hole is very, very small, okay, you can then approximate, or you can say that your hole is 0 to begin with, at the point very small, you can calculate that, very small due to minority carrier concentration. You can then approximate your J drift to be effectively equal to contribution by just electrons. Okay, so you can just forget this whole component because your P is very, very small. Okay, if you compare to your N times 10 to the 16, and your P is 10 to the minus 4. It's like 20 orders of magnitude difference. Therefore, you can just approximate your J drift to be contributed by only electrons. Then you can just replace all the parameters. Q is given, is known already. Mu is given, go back to the previous page, right? Mu for gallium arsenide is there at room temperature. For electrons, if it's asking for holes, then it's different story, 400. Ataupun if your P is not negligible, if your P is not 10 to the minus 4, say if your P is like perhaps bigger, 10 to the 5, 10 to the 6 perhaps, then it's going to be quite significant, the contribution of the holes to the drift current density and to the hole current density overall, right? So kalau in that case, is if your hole is like 10 to the 5, 10 to the 4, you need to calculate your J drift associated with the hole as well. Maksudnya, you kena tambah J drift electrons plus J drift holes, but you might come to the value that is very close to electrons because your hole might still be a lot smaller compared to contribution of electrons. But you still have to calculate because it's not very, very small. But in this case, since we are working with P in the region of minus 4, which is very, very small, then it can just be omitted in this case, right? So mu is given, ND is given 1016, and electric field is given 10 volt per centimeter. So therefore, your J drift is dominated by electrons, and that is given by 136 amp per cm squared. Okay, so let's have a look at the comment down here before we stop. A significant drift current densities can be obtained in a semiconductor applying a relatively small electric field. This is considered quite small, right? And we may note from this example that drift current density will usually be primarily due to the majority carriers in an extrinsic semiconductors. Typically, right? Typically, your J drift component will be dominated by one type of carriers, either holes or electrons, unless it's mentioned that your ND or NA is not that high. It is a majority carriers, but that is not that high. In this case, 10 to the 16 is considered high. If you say your ND is only like 10 to the 13 or 14, right, it's slightly dope, then the contribution from your minority carriers will be more significant. And in that case, you might want to calculate both components, right? Even though typically it's due to majority carriers. Right? Is it okay so far? Can you understand the concept of drift and the calculation here that we do? And the contributions from both components? Electrons, holes, why holes not around, why only electrons? Okay, anyone couldn't understand? Anyone miss out somewhere? Anyone lost halfway through? Semua paham? Good. Semua paham, then that's the best case, ideal case. Either semua paham ataupun ada yang tak nak beritahu. So if you don't tell me, then I wouldn't know. There's no way for me to know, right? I couldn't see your faces. I nampak your faces, then I could probably tell you are nampak ada kedut kat daya. Tak faham ke, ataupun you show a confused face perhaps. But now I couldn't see. And I couldn't tell. Right? Unless you tell me. Okay, so right. So now if you don't understand, let's just go back and try to do for yourself. Okay, try to work out for yourself. Very straightforward still, right? Very straightforward still. So we're gonna move on with conductivity tomorrow, resistance, and a bit of calculation as well. And then we're gonna move to diffusion. Right? If there's no questions, then let's just stop here. Bye bye. Take care. Assalamualaikum. Selamat buka puasa.